Hello again, let's continue our lesson on number system. On this video, I will help you learn how to convert any number to binary. So with any number, we mean decimal to binary, octal to binary, and hexadecimal to binary. So let's start with learning how to convert from decimal to binary. So the decimal to binary conversion is actually very easy. You just have to repeatedly divide the number by 2, and then the remainder forms the answer, and we read it from the bottom to the top. So let me give you an example. So for instance, remember that in the previous video we learned that to represent a number into its decimal form, you have to put a base of 10. So 25 here with a base of 10 means we're trying to convert from decimal to binary. So as said in the previous slide, to convert decimal to binary, you only need to repeatedly divide it by the base, which is 2. So 25 divided by 2, you get 12 with a remainder of 1. So you need to take note of the remainder in this sense, in this case, and then reject that as you continue dividing. So you focus on the whole number. So in this case, the whole number is 12. 12 divided by 2, that gives you 6 with a remainder of 0. So even if there is no remainder, you take note of the remainder. You set it as, you remember it as a remainder of 0. So you set it aside and then continue. 6 divided by 2, you get 3 with a remainder of 0. And then 3 divided by 2, you have 1 with a remainder of 1. Alright, now, and then you continue dividing. 1 divided by 2, you get a result of 0 with a remainder of 1. And so of course, because the whole number is now 0, you stop dividing. So in order to interpret this, you have to look at your remainders from the bottom and read it up. So our remainder so far has been, reading from the bottom to the top, is 1, 1, 0, 0, 1. So therefore, your decimal number 25 converted into binary is 11001. And that's it for our first example. For our second example, let's say that instead of a whole number, you have a decimal or a fraction, which is 0.265. Now in this case, because it's 0.265 and not a whole number, you multiply it by 2. So 0.265 times 2 is 0.53. Now unlike the previous example, in this case, because it's a decimal number, you have to take note of the whole number and focus on the decimal part. So in this case, the whole number is 0. You take note of that, or you put it aside, and then focus on the 0.53. So 0.53 times 2 is 1.06. So again, you focus on the whole number, you set that aside, and focus on the 0.06. Now 0.06. Now so the 0.06 times 2 is 0.12. So again, take note of the whole number, which is 0, and then focus on the 0.12. So 0.12 times 2 is 0.24, and the list goes on and on and on. So in this case, this could be infinite now, but you will just have to ask the faculty or the teacher giving you that problem as to how many digits would he or she want you for that particular conversion. So if in case your teacher says only 4 digit, so you stop here. Now otherwise, you'll have to continue multiplying the 0.24 by 2, and thereby getting the 5th digit. So in other words, as you can see here, the 0.265 in decimal form is converted into 0.0100 in binary form. Now that means to say, if in case you are given a problem that has a whole number and a decimal part, you have to divide the whole number by 2, just like the previous example here, and then merge it with the result of your computation in decimal form or in fractional form in this, as in the example shown here on your screen, which is 0.265. So in other words, if the number given to you for conversion is 25.265, so you have 11001.0100, and that is your binary form from 25.265 in decimal into binary. Okay, I hope that clears that part of our discussion. So please take note that in converting 25 here to binary, because it is a whole number and we are dividing it by 2, we read the result from bottom up, whereas in this sense here, because it is a fractional form or decimal number, you have to read it from top to bottom. So we're reading it from 0100 and not from 0010. Okay, I hope that makes sense. Okay, now the next conversion that I will discuss for this video is how to convert octal to binary. So to convert octal to binary, you need to convert it into its 3-bit binary equivalent. Now you need to remember the 3-bit representation, which is 4, 2, and 1. Now 4, 2, 1 here is very important. If you find it difficult to remember 4, 2, 1, you just have to remember that from the rightmost side, which is 1, you double it, it becomes 2, and then you double 2, it becomes 4. So you have 4, 2, 1 as your 3-digit. Now, in order to convert octal to binary, you have to remove the spaces afterwards. So you need to convert it one by one or digit by digit and then remove the spaces to put all those numbers together. So let me give you an example. So before we proceed to the actual problem, let me just share with you that in converting octal to binary, for example, because when we speak of octal numbers, you have numbers 0 to 7. This is actually the conversion. So remember your 4 to 1. So try to imagine that in order to get 7 in octal form, your binary is 111. Now why 111? Remember your 4 to 1. So 4 plus the second digit, which is 1. So that means to say that that's 2, and then the last digit on the rightmost side is 1. So in other words, your 3-digit 111 here represents 4, 2, and 1, and that is equivalent to 7. So 4 plus 2 is 6, plus 1 is 7. Now the next one is 6. So how do you convert octal into binary form, octal number 6 into its binary equivalent? Remember again, 4, 2, 1. Now that means the first leftmost digit here, which is 1, is equivalent to 4. The second 1 is equivalent to 2. And so 4 plus 2 is 6. Now this one is 0. So in other words, we forget the 1, which is the last, supposedly the last digit. Okay, let's have it one more time on number 5. So since you have 0 in the middle, that means only 4 and 1 are represented. So 4 plus 1 is 5. For number 4, remember again 4 to 1. Now since only 1 on the leftmost side is represented, no? So that means only 4 is represented. So 4 plus and 2 and 1 are not represented here because it's being shown here as a 0, so that's equivalent to 4. Now again for number 3, remember 4, 2, 1. So since the first digit, which is supposedly for number 4, is 0, that means 4 is not represented, So 2 and 1 is 2 plus 1 is 3. That's why 0, 1, 1 is your representation for number 3. Now, how do you represent 2? Now, remember again, 4, 2, 1. So, the only 2 here is represented because the 1 digit is only in the middle. So, that's equivalent to 2. And then, of course, going back to our 4, 2, 1, you represent that as 0, 0, 1. That means that only 1 is represented. And that is now the equivalent in binary. That is now the equivalent binary form to your octal 1. And of course, 0, 0, 0 means the absence of 4, 2, and 1. So, it's 0, 0, 0 in binary form. So, in other words, when you think of 4, 2, 1, think of 1 as an on switch and 0 as an off switch. So, if you say 1, 0, 0, you have on for 4, off for 2 and 1. So therefore, only 4 is represented, and that is now the equivalent of 4. So I hope you get that logic very clearly. Again, let's go back to 6. So 4 is on because it's represented by 1. So that means 4. And then 2 is represented here because again it's represented by another 1. So it's on. So 4 and 2 are on. 1 is off. So 4 plus 2 is 6. Okay, now if you see 3 1s, it means 4, 2, and 1 are on. So therefore 4 plus 2 plus 1 is 7. I hope you got that correctly, or you got that, you understood that. Again, if 0, 1, 0, 0, 1, 0 is the binary number, that means only 2 is on, 4 is off, 1 is off. So 2 is this. So 0, 1, 0 is the equivalent of your octal number 2. So just remember 4, 2, and 1. Now let's start with our first number. So let's say that we're trying to convert 127662 in octal into binary. So of course, we strictly put a base of 8 on this number, and in order to convert it, we need to convert it one number at a time. So 127662, so try to put that into one column. So 127662. So remember your 4 to 1. So if you need 1, you only need to switch 1. So 0 or off for 4, off for 2, and on for 1. So that is now equivalent to 1. 4 to 1. So again, only off for 4 and 1, only on for number 2. So that's equivalent to 2. 7 is of course the sum of 4 plus 2 plus 1. So all three numbers makes it on. So we add 4 plus 2 plus 1, that's 1, 1, 1. That's equivalent, the equivalent binary for your octal 7. And then again, of course, it's 1, 1, 0 for number 6, because that will add up 4 and 2. And then another 1, 1, 0 for another number 6. And then 0, 1, 0 for number 2, just like your previous number here. So you just copy all of that together without the space, and then you put a base of 2. So that is now the equivalent of your octal 127662 to its binary form. Now let's move on to another number. Let's say you need to convert 662,543 from octal to binary. So that means we convert 6. So that's equivalent to 4 and 2. So 1, 1, 0, and another 1, 1, 0 for another 6. And then 0, 1, 0 for 2. And then 5 would be 4 plus 1, that's 4, 0, 4 or 4 and 1, so that's 1, 0, 1. And then of course for 4, that would be 1, 0, 0, and for number 3, that will be 0, 1, 1. So you add that, or you just write that together, copy that together, and put a base of 2. you now have your conversion from octal to binary. Now let's move on to the third one. So to convert hexa to binary, it's very close to how you convert octal to binary, but this time you have the fourth digit, which is equivalent to 8. So if you switch on 8, 4, 2, 1, that is now equivalent to 8 plus 4, which is 12, plus 2, that's 14, plus 1 is 15. So if you remember, 15 is equivalent to hexadecimal F. Alright, so you just have to convert it by using this binary 4-bit representation, 8421, very much like how you convert octal to binary. So just remember, if it is 0, then it will be 0, 0, 0, 0, meaning your 8421 are all off. Now if it is 1, that means only 1 for your 8421 digit is on, so that is only equivalent to 1. If you want 2 in hexadecimal, that means you only switch on the digit that represents number 2, so 8421, so that's 0010. And then for number 3, remember again 8421, so you only activate the digit that represents 2 and 1, so 0011. For 4, it's 0100, so 8421. So this 1 here is for your digit number 4. And then of course, if it is number 5, it's you're activating 4 and 1 here, so 0101, so that's 4 plus 1 is 5. And then here you have 4 and 2, that's equivalent to 6. And for 7, it's simply activating 4, 2, and 1, and of course switching off the digit that represents number 8. Alright, so 8 of course is 1000. 9 is represented by 8 and 1, so 8001. Letter A is equivalent to 10, so you need to activate 8 plus 2, so 1010. Now B is 11, so that's 8 plus 2 plus 1. C is 13, so that's 8 plus 4, that's 12. Alright, and then D is 13, so that's 8 plus 4, that's 12, plus 1 is 13. And then letter E is 14, so it's 1110, that's equivalent to 8 plus 4 plus 2. And then of course you have letter F, which activates all 4 digits 8421, that's equivalent to 8 plus 4 plus 2 plus 1, and that's equivalent to 15. So I hope you got that, you understood that representation before we move on to solving hexadecimal to binary. So as I said before, if the number given that represents hexadecimal is C62, you need to remember what is the equivalent of C. So remember 0 to 9, and then 10 is A, 11 is B, 12 is C. So convert the letters first to its equivalent. So C62 must be converted to 12, 6, and 2, and then individually convert these numbers into its equivalent, remembering the 8421 representation. So 8 plus 4 is 12. So this one is 4 plus 2 is 6. So 0110. And then of course for the representation of your binary, hexadecimal number 2, that should be 0010. So you only activate the digit that represents 2. And then put all of these digits together, from left to right, just like what you did with the octal, and then just put a base of 2. So your hexadecimal 1262 or C62 is equivalent to 110001100010. Alright, so let's move on to the next example. If it is 8EC, you need to convert that into its actual number equivalent. So 8 is as is, E is equivalent to 14, C is equivalent to 12. So convert this one individually. 8 is going to be 1, 0, 0, 0. So that's the representation of 8, okay, as an on number. 14 is 8 plus 4 plus 2, alright, and then 12 is 8 plus 4. So you just put them, copy them together from left to right, and then add a base of 2, and that is now your equivalent conversion from hexadecimal to from hexadecimal to binary. Alright, so in summary, we have learned how to convert decimal to binary by repeatedly dividing the number by 2 and reading the remainder from bottom up. Remember that if it is the equivalent in decimal form in binary, and rather decimal to binary, you have to continuously multiply it by 2. Alright, and read it from top to bottom, and then wait for instructions or ask your teacher if it's not indicated in the exam as to how many digits would she or he want you to convert that number into its binary equivalent. Now for octal to binary, you just have to remember the 4-to-1 representation. So again, 111 is equivalent to 7 because it's 4 plus 2 plus 1. And 010 as an example is equivalent to 2 because that means only 2 is activated. So think of 1 as on, think of 0 as off, and then put that in place, arrange that in your brain, in your when you analyze the numbers as 4, 2, and 1. So it's just a matter of switching it on and off. Alright, so for hexadecimal to binary, it's very similar to octal. You just have to remember the 8, 4, 2, 1 representation. So if you need F, that's equivalent to 15, so that's 1, 1, 1, 1. Okay, if you need 4, if it is hexadecimal, therefore it should be 4 digits, so that should be 0, 1, 0, 0. Alright, okay, so I hope you understood the discussion of all of those numbers converted to binary. Thank you, guys.